Okay, if you're giving us a clock question, we're going to be working with radian angles again, we'll compare it to degrees. Giving us a clock, they said it's exactly 3 o'clock and 25 seconds, so we just kind of estimated where the second hand was. Okay, pointing down. A minute has not passed since 3 o'clock, only 25 seconds have. They've told us that the second hand, which we've drawn in red, is 9 centimeters long, and it's actually directly below the hour hand. So we're actually going to, I'm going to delete this part. We're going to stretch this a little so it's directly below. So they've told us that the hour hand and the second hand tips are directly below each other. In other words, making a right angle triangle, okay? So let's set up a Cartesian plane here. We'll just change the color of it to something that's a little easier for us to see. So here's our x and our y axis, let's say, okay? So they've hit at the origin here. We know that this measurement here is 9 centimeters, okay? So what we're going to have to do is figure out some of the angles in this, okay? Now, technically, 25 seconds is at, this is good. We have to break the clock into fractions, okay? So let's think about our seconds. Let's fill in the rest of the clock. This would be 1, 2, 3, 4, 5, right? Okay, well, let's think about 25 seconds. In terms of seconds, this is 5, right? This is 10. This is 15. Oops, spell seconds, right? This is 20, so we've clearly pointed this at the wrong one, right? Because they said it's at 25, okay? So let's point this a little better, which means we're going to have to extend this a bit. Just fine. That's 25, okay? So this is fine. We'll pull it down a little farther, okay? So here's really what it should look like, because that's at 25 seconds. Well, these are fractions of a clock, right? Because a clock is circular, let's go to page width. Because the clock is circular, what has happened here is our angle, our degree here, is a fraction of the clock. Okay, so one way you could look at it is we're used to looking at our system going back this way, okay, which is really fine. Okay, sorry, let's do that again. We're looking at going back that way. Let's do that again. Okay, so let's actually go back to what we're used to doing, and then we can talk about the reverse of it. So what this really is we know. Let's go to radian measurements, right? This would be half a pi, this would be a full pi, this is 3/4 of a pi, and all the way around would be 2 pi, but we haven't gone all the way around. Let's think of it as a fraction of the clock. This is a quarter. We've gone past 3/4, and then this here, they split this fraction of the clock, okay? So from here to here, they split it into 1, 2, 3 major parts, right? Because if you think about it, what has happened here is, let's say we're just talking about past that 3. Well, this is 1/3 of the way, this is 2/3 of the way, and this would be the full movement path, right? So they've broken this up. Now, in terms of an actual clock, these are in 12ths, okay? This full clock is in 12ths here, so we have 7. Oops. 7, 8, 10, 11, okay? Now, we talked about it in thirds because we were just talking about 1/4 of the clock. Right? But technically, we have to talk of the whole clock as a whole. So because we're in radians all the way past here, we need to figure out, what that is. Well, each of these movements is 1/12. Okay? So it's directly at 5. So from the 12, it's actually 5/12 away. Okay? But because we're going in the reverse, when we do the reverse, let's think of it as 12ths. Well, this here would be 3/12 of a movement, okay? Around here would be 6/12, which would be half. Here we have 9/12, okay? Is this making sense so far? Let's break it again. So this would be up to here, would be 3/12 of the clock in terms of the fraction. Up to here, we would have 6/12. 6/12 of the movement. To here, we'd have 9/12. And here, we actually have an extra 12th, right? So this would be 10/12 of the way, okay? But what we also got to do is we got to break that into radians, okay? That's not how our radian measurements are set up. That's just fractions of the clock if we go back this way. So if we're talking about radian measurements, well, this here is actually half pi, right? T here is a full pi. Good. T here is 3 over 2 pi. Okay. Now, this has been broken up 3 over 2 pi. What would a 12th of a movement be considered on this type of thing here? Well, we're going to have to actually break it into this. Okay. So let's talk about that for a second. How we're going to break it into our actual radians that we're used to using here. We have 3 over 2 pi. So in other words, this is a full pi movement past it. Now, we have a couple other ways of looking at this. Let's talk about it for a sec. Okay, so what we just quickly did on the side, and we'll talk about it, is we knew that this was a 12th of a movement, and up to here was 3 over 2 pi, right? Well, we know we had 3 over 2, and we had to add a 12th of a movement. We needed a common denominator, so we turned the 2 into 12, which means we had to multiply by 6, which means we had to multiply 3 by 6, which gave us 18 over 12. So in terms of radians, that's how far up to here, the 6 o'clock would be 18 over 12. We know we went a 12th of a movement more, so we had to add 1/12. Well, with the common denominator, what that gives is 19 over 12 pi, okay, in terms of up to this point here. That's what we got. So that's starting here all the way around to here is 19 over 12 pi. So let's talk about this. I'm going to bring the triangle around. Looks something like that. We know that this is 9 centimeters. And we know that from here to here is 19 over 12 pi. Okay? Well, what we're trying to figure out is this distance here, right? We know this is a right angle triangle. So to make this a little easier for ourselves, it's probably best if we just find out what the rest of this angle is. Okay. Well, one way we can do that is we know, and I'm going to do this in green, a full rotation around the circle is what in terms of pi? 2 pi. Okay. So we know the whole way around is 2 pi. We can subtract the distance we've gone to figure out what our answer is going to be. So 2 pi subtract 19 over 12 pi. Okay. Again, we're going to need a common denominator, and that's going to give us our angle in black. We'll call that theta. Okay. So that will give us our theta. Well, in order to have 2 pi with a common denominator, that's 24 pi over 12. Subtract our 19 over 12 pi. What is our theta going to be? 5 over 12 pi. Okay, so that's how many movements we have left. 5 over 12 pi. Okay, that's what that little angle in there is going to be. So we'll keep this in radians. So now that we have that, what we have is our triangle again. We'll redraw it. Okay. You know, it's not 100% accurate in terms of size, but this in here is 5 over 12 pi. This distance here is 9 centimeters. We need to find this. Okay, so in terms of the angle, trigonomic ratio, what do we have? What's hypotenuse. Hypotenuse and adjacent. So which of the ratios are we looking for? To use cos. So cos 5 over 12 pi is equal to adjacent, which is our x, over hypotenuse, which is our 9. Well, we need to get x by itself, so it becomes 9 multiplied by cos 5 over 12 pi. So we have to put our calculator into radians here to figure out what the hour hand is. So make sure you're in radians and give that a try.
Uh, 2.32.
2.32?
Yeah.
Okay.
Oh, I'm sorry, 2.32, yeah. Okay.
Yeah, okay, centimeters. So in other words, the hour hand is 2.32 centimeters, which makes sense. The hypotenuse is 9. It's far less than that. That's probably a pretty logical answer. 2.32 centimeters is our distance.